Okay, folks, getting into this next learning goal on the kinetic salt effect. This is a bit complicated in the math, but I think there's a really cool qualitative result that I really want you to be more familiar with than the math itself. All the same, let's go through it. And hopefully this reaction looks somewhat familiar to you. This is our same transition state theory reaction where an A and a B can react to form some transition state, and that transition state can get kicked back out to reactants or can go forward into products. The only difference being now, you can see there are charges. So plus or minus Z is the charge of the ion. And we'll notice here that C is also charged, and I actually forgot to do two things. So C is going to be the sum of the charges of A and B, right? But this is also getting a double dagger, so it's plus minus and double dagger, indicating that it is a charged transition state. And if you recall, if we approach this in our normal kinetic way, looking at the formation rate of product dP by dt, if I put a K double dagger over the second reaction to indicate the rate constant of this reaction is K double dagger, then we can write dP by dt as K double dagger times the concentration of C double dagger. And I'll omit writing the plus minus on C for ease of writing. Okay, so we note that we could write the equilibrium constant of this first reaction. So I'm going to give this a big K double dagger as the following. So right, this is our equilibrium constant. So that's going to be the activity of C divided by the activity of A. And then those are all charged. I'll just drop right in the charges to make this easier to write, over the activity of B. And just as some reminders, recall the activity can be written as the activity coefficient times concentration. So let's go ahead and write that down as well. So now the activity of C double dagger can be written as gamma C double dagger times the concentration, all divided by gamma A times the concentration of A times gamma B times the concentration of B. And we can do some arrangement here to find a suitable expression for the concentration of C so that we can put it in this dP by dt rate law. So now just doing some algebra and writing this directly, I'm going to collect all of the concentrations. Let's see, sorry, I'm rearranging this so this equals big K. All right. So the concentration of C still equals big K. So I'll do the algebra and then we'll make some simplifications first. So then multiply by the bottom, right? So that's going to be an A times a B. And here I'll separate out all of those gammas. So that's gamma A times gamma B. And then that will be divided by gamma C double dagger. Okay, so now I'll note here that all of these gammas, so I'll write that the equilibrium constant with respect to gamma, only with respect to gamma, right, will be gamma C double dagger all over gamma A times gamma B. So you can see we've got 1 over that right there. But if we plug that into this expression, right, we're going to end up with the following: dP by dt equals, we've got that as K double dagger, and now that's multiplied by big K double dagger times A times B. And now we've got this whole thing going on. I'm going to combine it with our other equilibrium constants and note that that's all divided by K with respect to gamma. So you can see what we end up with here now is dP by dt equals this collection of the rate constant and equilibrium constants multiplied by AB. So what that means is this collection of everything right here, I'm going to call K Rxn. This collection of equilibrium constants becomes our effective rate constant. So let's keep going with that. So let's remember dp by dt, right? That was little k double dagger times big K double dagger times A times B, and that was all divided by big K gamma. So there's a couple ways that we can approach this. So when our activities are equal to 1 or very close to that, so when we're under this dilute regime, we can replace the activity coefficients with their ionic strengths. And right, if you recall here, the log of gamma is equal to some fit coefficient. So some fit coefficient, right, which we can determine with data, times the charge times the ionic strength. Okay. So now what that, and another way that we could state that is when that is the case, K, so big K double dagger can just times the, the little k double dagger. This I'm just going to call KRXN standard. So we're just replacing that whole top half with KRXN standard because that is the standard value, right, when the activities are equal to 1. So now I'm going to write K reaction equals K reaction standard all divided by big K gamma. And it's convenient to write this in terms of logs because we have the logs all right here. So I'll go ahead and do that. I'm going to write this as the log of K reaction equals the log of K reaction standard minus the log of big K gamma. And so now we'll see why the convenience here of keeping these with logs, because now I have all of these as logs. And instead of putting this together with products divided by reactants, we can just take advantage of the fact that multiplications in logs are a sum and divisions in logs are a subtraction. So rewriting that now, the log of the overall reaction ends up becoming the following. So we still have the log of KRXN standard, so when everything is in its standard state. And then now replacing this, so negative log of K gamma, I'm going to subtract the value for the product because it's a division, and I'm going to add the values for the reactants because they're multiplications. And I can also do a little bit of algebra. So I'm going to do some algebra along the way. And I'm going to collect that fit coefficient, A, out in front. Oops, let me make a better looking parenthesis sign there. So now we first start with, so just backing up, K gamma was gamma C divided by gamma A times gamma B. So if I do the log of K gamma, that just becomes the log of gamma A plus the log of gamma B minus the log of gamma C, right? So doing some algebra and plugging in like terms, we'll assume for now that the ionic strength is the same for everything so that we've got the same concentrations. And that means now in substituting out of A, we've got ZA squared. A and I will both be taken out, plus ZB squared. And remember, Z's are the charges. And then now minus, we've got to do the product. And the product, recall, will have the charge of A plus B all squared. And then, of course, that is times the ionic strength. And now I'll do just a little bit more algebra, and we'll be able to see the qualitative aspects of this equation. So it goes log of K reaction times log of K reaction standard. And I'm just going to do a little bit more algebra. I'm going to write that as plus 2 times A times ZA times ZB all times the ionic strength. So some of these Z's we were able to collect and do the algebra on. Okay, so I've got that equation written right here. So here's the equation we just derived. So I know it was a little bit of a wonky derivation. But importantly, what I want to point out, we get some unexpected results from this thing. So let's look at it. So if A and B have the same sign, the reaction becomes faster with increasing ionic strength. That's weird, right? We would normally think like 2 positive ions or 2 negative ions reacting with each other would result in a slower reaction, but it's in fact the opposite, right? So think about the way that this math is going to work. If A and B both have the same sign, then this quantity turns out to be positive, which increases the overall value of the rate constant. So again, if A and B have the same sign, the reaction becomes faster when we increase the ionic strength. So it's not to say that 2 positive things or 2 negative things react fast. They might. What we're really saying is if we increase the ionic strength of those 2 things and they have the same sign, they will react faster. Okay, formation of a singly highly charged ionic complex from 2 less highly charged ions is favored at high ionic strength. So again, right, if this is a +1 and a +1, and we increase the ionic strength, the reaction gets faster. However, if this is a +2 and a +2, and we increase ionic strength, it gets even faster. So you can see that with these graphs here, right? So this means a faster reaction going up this way, and this means a slower reaction going down this way. So this, basically, if we subtract that over and recognize, once again, the subtraction of logs is a ratio, right? Then positive numbers on this graph means faster reaction, negative numbers on this graph means a slower reaction. And so again, you can see here, if it's +1, +1, it gets faster, but not as fast as if it's +2 and +1, or even +2 and +2. And we would similarly see that if it was minus and minus, 2 minus and minus, or 2 minus and 2 minus. So that's an unexpected result. And now, as you might imagine, ions of opposite charge react more slowly in solutions with high ionic strength. And that's because if now we've got a positive times a negative, this value gives me a negative, and overall that will slow down the rate constant according to the math. And we see the same thing here. If we've got a 0 and a negative, or a 0 and a positive, there's overall no change in the reaction, because by putting 0 on any one of those charges just drops that term right out, and the reaction proceeds as fast as it could proceed under standard conditions. But now, as you can see, if we go positive, negative, positive, 2 negative, 2 positive, 2 negative, etc., that greatly slows down the reaction with increasing ionic strength. And part of that is due to the attraction those ions have with the spectator ions not present in the reaction, right? Those spectator ions are going to have an influence on these reactants as ionic strength is increased. Okay, folks, I'll see you in the next video.